This video, we're going to go through questions 1 and 2 from activity 4B of your textbook to have some work solutions in case you got stuck and you need some help, or you just want to verify the process of how you got to your answers and check that you got it correct. Okay, so let's look at question 1 first, and then we'll go on and look at question number 2. 1A, we've got two speakers placed 2 meters apart. Okay, that's a really key point of information there. We've got 2 meters apart. We know the frequency, F, that they are operating at. That's quite hard to read. F. Okay, and we'll just note that because we're looking at speakers, probably we're going to be interested in the speed of sound at some point. Okay, now for part A, they want to know the wavelength of the sound. All right, so let's see if we can do that, shall we? A. How do we calculate wavelength? We know we've got a V equals 330. We've got D, our separation, 2 meters. We know we've got F equals 660 hertz. Okay, and we're trying to find lambda. Lambda is our unknown. Okay, so what equation might we use? I think we should try and use V equals F lambda, our wave equation. Okay, wave equation. This one's super good, nice and easy to use, and we're trying to find lambda. Now, do we know V for our wave? Yes, we do. We know the speed of sound, and we know F, the frequency of our wave. Yes, we do, 660 hertz. So we can go ahead and hopefully find lambda really easily. Okay, lambda equals V divided by F equals 330 divided by 660 equals 0.5, and we know wavelengths come in meters. We know that because we put meters into our equation, all right, up here, 330 meters per second. So we get meters out the end. Okay, great. B. When walking along a line in front of the speakers, a series of loud and faint sounds are heard. Explain why. All right, we could draw a diagram to help us understand if we like. I'm going to sketch it really badly on the diagram given in the question. We know out of each speaker we get a wave, okay, and the wave comes out, nice big circular wave front, okay, and it comes out the same of both, which is really important. Same wave out of both speakers, off into infinity. Okay, and hopefully you're better at drawing than I am. Now, if we chose some path through here and we were to walk, okay, if we walk through here, we're going to hear a pattern of loud and quiet and loud and quiet, and we can see why. Okay, now let's try and write in words what's going to go on. P. As walking through, we will encounter, come on, nodes and antinodes. Okay, we're going to find nodes and antinodes. That's great. We absolutely know that. All right. How can we describe what we should probably describe what a node is? Okay, and relate that to our diagram. Nodes are out of phase by 180 degrees and are quiet. Nice. Antinodes are in phase, or if we want to say the other way around, 0 degrees out of phase and are loud. Okay, seems good. Zero amplitude, zero amplitude, zero loudness. Okay, this was our max amp. You want to just put that in there as well. Quiet. These are our zero amplitude Okay, so that's where we've got a nice flat line and we're getting no sound produced. It's been cancelled each other out and it's nice and quiet. Okay, let's look at C, shall we? At point P, the second loud away from the center is heard. What is the path difference from point P to the speakers? Okay, so we can think about this really easily. I think we can understand using the relationship we developed through our interference worksheet, or we can try and calculate it if we prefer. Okay, so we get C. We know we're at the second loud. Okay, so what N is the second loud point? N equals 2. Okay, remembering up here, N equals 0, and then N equals 1 on the way out. Okay, so N equals 2 is our second loud point. We know we're at a loud point, so we're at an antinode. So PD equals N lambda. Nice. Okay, so PD equals 2 wavelengths, and we know the wavelength equals 2 times 0.5 equals 1 meter. Just like that. Bam. Not so hard. Okay, and then C, or D rather, calculate the angle at which point P is found. Okay, so we're trying to find theta. We know N equals 2, we know lambda equals 0.5 meters. Okay, and what's the equation that we're going to need? It's the one that we had in our other worksheet, our quiz. N lambda equals d sine theta, I think. N lambda equals d sine theta. Okay, and by writing that down, I realize we also know d, which is this value up here. D equals 2 meters, because the speakers are d meters apart, they're 2 meters apart. So d equals 2 meters. Nice, and we're trying to find theta. So what we're going to do, we're going to move d onto the opposite side. We're going to divide by d, both sides by d. Okay, these ones will cancel out. We're going to get sine theta equals n lambda over d. Theta equals inverse sine of both sides. Whoops. 1 n lambda over d equals inverse sine 2. Whoops. 2 times 0.5 divided by d. Which was 2 meters, equals 30 degrees. All right, done, 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 and done. That's question 1 complete. Let's now look at question 2. Question 2. A laser produces red light with a wavelength. Nice, we've got a value already, wavelength. Okay, we know already lambda equals 6 times 10 to the negative 7 meters. That's awesome. Forms an interference pattern shown through 2 slits 0.1 millimeters apart. So that's D. Okay, that's that part there. It's our slit separation, but we've got to turn it into meters. All right. And we know it's going to be 0.0001 meters, I believe. Hopefully I'm not wrong about that. We will see in a minute. Okay. And we know one other value. We haven't started calculating yet, but we know the pattern is a screen 2 meters away. So we know L equals 2 meters. All right, nice. So, I, part 1. Okay, what is the spacing of the fringes on the interference pattern? So we want to know X. X is fringe spacing. Okay. And what's our equation that we can use to calculate this? We, in lambda, in lambda equals dx over L. I'm just going to pause for 20 seconds while I remember that for a second. Just check that's right. Yep, no, that's cool. We know that. And we want to find x. Okay. Now, we can do this for any fringe that we like. Okay, we can do it for the first, second, third, fourth fringe, it doesn't really matter. We'll do it for the first fringe because that lets us say that n equals 1. So the first fringe, whoops, that's not Hasper fringe, has n equals 1. Okay, so let's look at this equation. Do we know n? Yes, we do. Do we know the wavelength? Yes, we do. Do we know the separation of the slits? Yes, we do. Do we know the distance of the screen? Yes, we do. And there's the thing that we're looking for, x. So let's rearrange this equation, shall we? We're going to start by timesing both sides by L. On both sides, we're going to get n lambda L equals dx, and then we're going to divide both sides by d. Okay, divide both sides by d. We're going to get x equals n lambda L over d. Let's go ahead and do that. 1 times 6 times 10 to the negative 7. I'll try that in brackets just to be really clear. Times by L, which was 0.1231 meters. Divide by D. The split, wrong value, sorry. In lambda L, where L is the distance from screen and source, which is 2 meters, times by 2. Right, 0.0001. Okay, and hopefully we should get 0.012 meters. Down the bottom. Fringe spacing of 0.012 meters. So the bright lines are 0.012 meters apart, if we want to say that in words. Okay. Second part. How many significant figures are there in the answer? Okay, so let's look at the data that we've got to help us answer this. Okay. How many significant figures? Oh, I didn't write a whole number here, which will be a problem. This is 6.0. Okay, how many significant figures does our wavelength have? It has 2SF. The 0 is significant. How many significant figures does our slit spacing have? The answer is, again, 2SF, if you can write that I can't. Okay, we read our data again. There's a 1, 0. That 0 is important. I'm getting too simple. 2SF again. Nice. Okay, again, 2.0 meters. Okay, that's 2SF. This is me being a bit funny. Okay, and n is just a number. Doesn't have figures. It's just a whole number. Okay, so all of our data has 2 significant figures. A part 2, all data has 2SF, so use 2SF in answer. Great. Cool. Done. And the last part we've got to do is state the assumption that has to be made for the calculation in part A, I. Okay, oops, we'll do that in blue. B. What's the assumption we've got to make? What do we think? What equation did we use? We used n lambda equals dx over L, which is only true when fringe spacing is very small compared to L. Okay, in other words, when theta is very small. Okay, that's our assumption. Only true when theta is very small. All right, I hope that helps.